Welcome to this explainer. Today we're doing something that honestly sounds a bit like pure science fiction. We are going to transform a standard everyday PC into a quantum-ready machine.
Now you might be wondering, can my regular home PC really run quantum code? Or maybe you're thinking, is this whole terminal setup going to be absolutely terrifying? It's a completely fair question. A lot of beginners feel incredibly intimidated by dark terminal screens and, just hearing the word quantum is enough to make anyone nervous. But today, we're going to completely demystify this entire setup process. We're going to build a professional-grade workspace from absolute scratch, step by step.
To make this super easy, we've broken the setup down into 3 really manageable phases. 1. Anaconda cleanrooms. 2. VS Code integration. And 3. Quantum code execution.
We have a clear roadmap for this journey. We'll start by installing our core tools, then we'll link those tools right into our code editor, and finally, we'll write and execute real quantum logic together.
All right, let's jump right into phase 1, Anaconda cleanrooms.
So, right out of the gate with a shiny new version 26.3.2 Conda setup, we immediately hit our first mini-boss. We try to make an environment and boom, we get an error saying create isn't recognized. Well, why did that fail? Actually, it's just because we typed create instead of Conda create. It's a highly relatable typo, but it teaches us a vital lesson right away. PowerShell doesn't know what create means on its own. Every single Conda command absolutely needs its proper Conda prefix.
This brings us to the concept of a clean room, which is absolutely crucial for managing multiple Conda projects. Imagine one workspace, let's call it QML1, that is completely empty, no Python, no packages at all. Then imagine another, like My Environment, which is our heavy-duty machine learning engine. Isolating your empty workspaces from your heavy-duty environments prevents nasty library conflicts down the road, and it's just a total best practice in daily machine learning workflows. Whatever you install in one stays completely isolated from the other.
Think about a massive 154.4 megabyte payload downloading right into that My Environment workspace. That payload brings in Python version 3.14.4 as the engine, NumPy 2.4.6 for incredibly fast matrix math, and Pandas 3.0.3 for heavy data analysis. It even pulls in Intel's math kernel library to make your processor crunch numbers at lightning speed. You literally need this kind of classical horsepower to eventually drive our quantum tools.
Moving right along, let's hit phase 2, VS Code integration.
Okay, so we open up our code editor, ready to code, and suddenly we face our second major trial. Why on earth is Conda suddenly invisible inside the VS Code terminal? You get this nasty PowerShell error screaming that Conda isn't recognized, even though everything worked perfectly a minute ago in our Anaconda prompt. VS Code actually opens its own completely separate terminal, and it doesn't just automatically inherit those Conda settings.
To defeat this error, we just need a precise 2-step combo to initialize it correctly. First, we change VS Code's settings.json to use the standard command prompt instead of PowerShell. Second, we hop back to our Anaconda prompt and run conda init cmd.exe. What that does is permanently write Conda's path right into the startup configuration. After a quick restart of VS Code, our terminal finally shows that beautiful base tag. Conda is officially live in our editor.
Now for the really crucial part, manually linking VS Code to that specific virtual workspace we built earlier. By pressing Ctrl plus Shift plus P and selecting our My Environment Python interpreter, we are explicitly telling VS Code which exact engine to use. And this is a game changer. It instantly grants us intelligent autocomplete and real-time error detection, seamlessly integrating our cleanroom into our daily development workflow.
And that brings us to phase 3, quantum code execution, the really fun part.
But hey, before getting to the quantum realm, we have to verify our classical engine is actually humming. So we write a quick file called test.py. We import NumPy as NP, import Pandas as PD, and whip up a simple data table. Run it, and it works flawlessly. This verifies our classical engine is perfectly crunching basic arrays and data frames. The foundation is totally solid.
Next up, we take the massive leap. We run pip install Qiskit. This injects IBM's Qiskit straight into our environment, which is literally the world's most widely used open-source quantum computing framework. Once that's installed, we can write a command like quantum circuit, too, to actually simulate quantum math directly on our standard classical CPU.
As we initialize those 2 qubits in our code, let's take a quick second to de-jargonize exactly what we're creating. A qubit is basically the quantum equivalent of a standard classical bit. But here's the wild part.
Unlike standard computer bits that can only ever be a 0 or a 1, a qubit has this mind-bending ability to be both a 0 and a 1 at the exact same time.
And that brings us to the absolute magic of our next line of code, the Hadamard gate, which we write as qc.h of 0. This tiny line throws our first qubit into a wild state called superposition. This means our qubit is now literally 50% 0 and 50% 1 at the exact same time. It exists in this fuzzy cloud of probability until we force it to decide by measuring it.
Finally, we apply what's known as a CNOT gate, typed as qc.cx of 0, 1, to entangle both of our qubits together. This creates a Bell state. Those two qubits become permanently linked, perfectly mirroring each other's states regardless of distance. It's exactly what Albert Einstein famously referred to as spooky action at a distance. And think about it, you just wrote the code for it on your home PC.
To actually prove it worked, we run a state vector simulation on our CPU. The resulting data shows a perfect 50-50 split in the probabilities, which proves that our qubits are perfectly entangled. We have exactly a 50% chance of measuring two zeros and a 50% chance of measuring two ones. But there is a flat-out 0% chance of them ever being different from one another. No 0-1, no 1-0, just pure, spooky entanglement.
Well, you did it. You navigated those annoying terminal errors, you successfully separated your Conda cleanrooms, you integrated your workspace flawlessly into VS Code, and you simulated actual, real-world quantum entanglement. You successfully built a professional quantum machine learning environment entirely from scratch. So now that you've totally leveled up your PC and conquered this setup journey, the only question left for you is, what incredible quantum mysteries are you going to build next?